All right, so this is the last lecture for system software for this semester. If you don't know already, the final exam is in 2 days at this time in this room. The project is also due at that time. Sorry that this is sort of so compressed, but we had the storm in the beginning that sort of pushed back some due dates. Yeah, so let's finish up the review for the final. So I didn't give the exact final, but it's like really, really close. The first several of these are going to be multiple choice questions. Probably about, let's see, like these are the multiple choice questions. The rest are open-ended. This is what your final exam answer sheet will look like. 10 multiple choice, and then several 10 open-ended questions. Nothing too in-depth. You have to be able to, do the regular expression to NFA, NFA to DFA, not on a very complicated expression, very similar to what we reviewed last time. Be able to do parse trees and type checking, be able to do the symbol table. Yeah. So you all got this, right? Did I send this out, right? Okay. So last time we covered, well, just to go over quickly, but we sort of covered the first half of the semester last time. Yeah, any particular questions from last time? The lecture video should have been up at some point. I think over the weekend I put it up. Any questions on this? Okay, so what's the difference between DFAs and NFAs? Anybody want to take? Anybody want to answer? Yeah. Yeah. So more precisely, there's only one transition for any given state and input symbol. So if I give you an NFA, can you create a DFA out of it? Yes, no? What do you think? Who says yes, you can create a DFA out of it? Who says no? Some people say no. So you can always do it. You can always create a DFA out of an NFA, and vice versa. Because, well, okay, if I give you a DFA, can you always create an NFA out of it? Kind of a trick question. Yes. Why? It already is. It already is one. So all DFAs are NFAs. But yeah, all DFAs are NFAs, and you can always convert an NFA to a DFA because you have a finite number of states. So what's the definition of a finite automaton? What things you need in order for it to be a finite automaton? Yeah. Number of states, its alphabet, transitions, starting state. All right, which of those are infinite, which of those are finite? They're all finite. But what about the language that it describes, infinite or finite? So can I have a DFA or regular expression that recognizes an infinite set of strings? Yeah, because clean closure, 0 or more, infinitely. Okay, we went over tokenizing. Let's see, where was this? Yeah, we went over tokenizing last time. Any questions on that? On like the tokens of a simple C program? Questions on that? Yeah. What kind of questions do you ask on the exam about tokenizing? I would say just what I said last time. Here's a program. Pick out pick out the tokens. Circle the tokens. How many tokens are there? Is this a token in the language? Simple C. So you kind of you have to know simple C, but it's very close to C. Make sense? Okay, let's see. All right, so tokens. Writing LFNIR for simple C stuff. So we did some arithmetic expressions last time. I think we covered arithmetic expressions last time, right? Questions on that? You're given an arithmetic expression, could have variables in it, could have nested stuff, could have parentheses. All good on writing LOVMIR for that? What are your questions on that? You make a parse tree, do a parse order traversal. Each time you reach an inner node, that's an operation. That's one LLVMIR instruction. That's project two. Question? Question, yeah.
Could we be asked to do LLVM from any project? Like, could we have a function, for example, or will we just have control flow? Or...
Let's see. I didn't do any functions. Because functions is really just using LLVMIR. It's like a very direct translation. So no functions to the LLVMIR. But yeah, control flow, arithmetic expressions, and loading and storing variables. So want any review on loading and storing variables? So it's just like any other factor, except if you see a symbol, you have to look it up in a symbol table. And I'll be very flexible about what the symbol table looks like. Just the fact that you basically put in a store or a load in the right spot is enough. Yeah. Still just one type, all int type. And if it's sort of approximate LFEMIR, if you get the broad strokes right, that's okay. I'm not expecting you to be like machine perfect. Okay. Did we cover parse trees last time? Did we review that? I don't remember. Who wants to see doing expression parse trees? Raise your hand. A couple people. Okay. So let's do that. Let's review expression parse trees. All right. So we'll combine expression parse trees and variables in one shot here. So if I've got something like x times y minus, let's make this more complicated, x times y minus 1. And we'll make the parse tree for it. So I'll do a really simplistic version of it. You could certainly do the right recursive, all that business if that's more comfortable to you. So this first node, so we know we're going to have these leaves. The first node corresponds to which operation? Is it the subtraction or is it the multiplication? So if I were to draw, there's going to be some term on the left and right here. We know there's going to be some terms here. What is the operation going to be? Is it going to be multiplication or is it going to be subtraction? Well, we have parentheses here. So is it ambiguous? Who says multiplication? Who says subtraction? So it's multiplication because because of parentheses. I'll just do the rest of the parse tree so we can see what this looks like. Probably not wrong. So yeah, if you didn't have the parentheses, you would have the subtraction be the first production that gets derived. So that would be the first node in the parse tree. So this is like the subtraction node, and this is the this is the multiplication node. This is the subtraction node. Yeah. No, there is, but the parentheses override operator precedence. Because if you remember the grammar for this, did I have the grammar for this? Not there. Oh, we did do this last time. So this, if you remember the oh, sorry, you cannot see that. So recall that if we look at the operator precedence built into the grammar, the parentheses were made the expression a factor. The result of this became a factor. So that has highest precedence, just because it's the same precedence as any other factor. Yeah.
trees with the primes in it or no?
Yeah, you can do that.
Oh, okay.
You go for it. I mean, it's harder, so you don't have to. So you can just do, you can do this style. So actually, this should have been an E and then followed by T, but I'm going to make this simpler. Yeah.
Do we need to memorize that grammar?
Well, it's open note, so you can bring any notes you want. Just no digital stuff, unless you remove the Wi-Fi and communications chips, and show me that you've done it. Okay, questions on just like the tree itself for this. Questions on the tree for this expression. Okay. All right, so the way the intermediate code is generated for an expression tree is you do what? What is the what kind of traversal of this tree do we do? Post order traversal of this tree. So post order traversal of this tree is going to go to the left node for, well, in this we're going to do left and right first. That actually doesn't really matter for arithmetic, I don't think. So we do the left side. It turns out, we end up reaching a factor. Whatever the value of x is, that's going to be the left stand operation for this node, or the left operand for this node, which is the multiplication. And then we're going to explore the right side. The right side itself is an operation. So we have to recursively generate code for its intermediate operation. So I'll walk through that more slowly and show you what IR gets emitted when you do that. So we process this left tree, and when we hit this variable factor, what do we have to do when we see a variable? How do we generate code for a variable factor? What's that? We have to load. You got to load from somewhere in memory. So assuming that we have some symbol table that we can do a lookup, we're going to make a new temporary register and load from whatever that variable is going to be. And I know that there's supposed to be like types here, and there might be alignment in real world stuff, but the broad strokes here is that you're going to load from some address in memory, and X is a register that holds that address. So then we do the right side of this, and so what is on the right side? What's our right operand for this multiplication? So this is the right side of this multiplication. So we have to recursively generate code for this this operand. So to do that, we first generate code for the left child. The left child again is a variable factor. So we do for variable factor load. So tell me why we have. So in LLVM, why do we have to have different variable names? Does anybody remember for these registers? Like, could I do something like this in LLVM? Like have two assigns T2. Who says yes? We can do that. Who says no? Okay, good. Just making sure you're all with me on that. Okay, so we also have the load value of X from F, or value of Y from Y's address space. And then we do the right-hand child. Now in LLVM, you can't just like directly assign T3 to a number. So what'll end up happening is we'll create a new instruction that does the subtraction. So what is the left operand for the subtraction? T2. And the right operand is 1. We know, right? Okay, so now we have finished the left operand for the multiplication, the right operand for the multiplication. So what's the next thing we have to do? The multiplication for that. So that's going to be one more instruction. That's going to be multiplication, with all the NSW stuff. And what are the two operands for it? T1 and T3. So another way to look at this is that when you perform this post-order traversal, so normally in any post-order traversal, like say you're counting the depth of the tree or counting the number of nodes, you would take the process the two children and then attach the new attribute, whatever it is, maybe it's node height, to the parent. So in this case, the left factor here, its attribute, so to speak, is T1, and its parent is also T1 because it's just, it's not an operation, it's just has a single child. And on the right-hand side, the attribute, so to speak, of Y is T2, and the temporary variable for the subtraction is T3. That's like classic post-order traversal. But instead of computing the height of each node, we're computing which temporary register represents the value of that at runtime. So that's how we know what the two children of the multiplication should be. Questions on that? Does that make sense? So then, as I said, these would have two arguments, T1 and T3. And so this expression, according to our language, is going to be used inside of a print statement or inside of a if body or an if condition. And so the attribute for that parent node is going to be its temporary register that holds the value at runtime. All right, questions on this? Questions on this at all? What are your questions? Okay. Okay, so we did LLVMIR for arithmetic expressions. Let's see, what did we do last time? We did recursive descent, trees. We did that as well. We did DFAs and NFAs. Okay. All right, questions? Questions so far on any of this material so far? Any material from last time? All right, so this we covered. Any questions on regular expressions to NFA to DFA? Questions on that? Everybody's good on that? Yeah.
I'm still not 100% on how to get from an NFA to a DFA. I know you have to go through the NFA and...
Yeah, that's the subset construction algorithm. So that is... okay, so what do you anything specific?
Do you have to show every way you go through it for a DFA, or is it just one?
Okay. So the basic algorithm is in order to, so what's happening here is, since the NFA can be in multiple states at the same time, a DFA cannot. So if we want a DFA, a deterministic automaton, we take subsets of states in the NFA and just say, okay, well, the NFA can be in these 5 states at the same time. So I'm just going to make a new automaton where those 5 states are represented by one state in the new finite automaton. We can do this because the NFA has a finite number of states. And so there's a finite number of subsets of states. So because of that, any DFA we create that corresponds to different subsets of that will also have a finite number of states. It may have many more states than the NFA, but it'll still be a finite automaton. And so the idea is you just step through each combination of NFA state and symbol in the language and see which state transitions you would make in the DFA. And the way that works is, if we're on a state that has epsilon transitions, then we include all of those epsilon transitions in our subset of the NFA states and call that one DFA state. this doesn't have an example of it, but if there were multiple transitions from the same symbol, those would be part of, when you transition on D from state 1, there would be multiple possible next states. So that would be part of the subset for the state you transition to. Does that make sense somewhat? So the way you do the construction is, you can also just try to do this sort of intuitively. You can sit down and figure out what the DFA would be from the NFA. But the mechanical way to do it is, you start on the first state, do the epsilon closure, which just means add any states that you can transition to through an epsilon to the subset. And then for that new subset, see for every symbol in the language, see what subset you transition to. So for state 1, that's, there's no other states in that subset. But when we transition to state 2, there's all these states that you can reach via epsilon. And so those become one subset of states that the NFA can be in at the same time. And we turn that into a single DFA state. Yeah.
So that is the accept state here. So would anyone in the DFA that contain 10 be an accept?
Yes, that's right. Yeah. That's a good question. So what is the initial and accepting states for the DFA? So as long as something in that set contains the accept state, then you accept. And so that's, in the NFA, the way that works is, if we think about what the original regular expression for this was, which I think is it's somewhere. I think I erased it last time. But if we think about the original regular expression that we were doing here, I think it was something like, this must have been D followed by, what was it, B, C, or A star? I think it was that.
Yeah.
So if you notice here, D by itself can be part of this language. So even though in this NFA, if we're in state 2, we're also in state 3, 4, 7, and 10. Even though we are in all these other states, we could have been in state 10, which means the string is accepted. And that matches the semantics of our regular expressions, which say if you just see by itself, then that's a member of the language described by the regular expression. So it's sufficient to just have one of the states. So you think of the NFA as sort of speculatively checking the input to see if it matches any path through the NFA. But only one of them has to succeed in order for it to be a match for the language. But yeah, it's a good question. Does that make sense? Does that make sense for the construction? Okay. Other questions? Questions on this? Yeah.
Will we be doing a DFA to regular expressions?
No. There's no question on that. Somebody asked that last time as well. Nope. There's no such question. Okay. That's probably some of the more tricky parts. This is like discrete, preparation for discrete too, if you're not already taking it. Okay, let's see what else we have in here. Okay, so we did, control flow. So I did put functions here, but there's not going to be functions on the exam. We did variable usage, variable assignment. So how do we do variable assignment in LVMIR? Just a store instruction. Okay, what about control flow? Should we go over control flow? LVMIR for control flow, like project 3 or project 4? Project 4? No, project 3. Okay. All right, so let's do a quick example. Well, actually, was the kind of like canonical example that I showed. So this branch and label is part of the if statement. And then if you recall, anything that's in the body, you just dispatch code generation to the statement parser, so statement code generator, parser and code generator. And then the next branch and label, those are part of the if then else statement, whereas the stuff inside of it is just recursively parsed, and code is generated for using those recursive descent functions. Okay, so you won't necessarily have to draw a tree, but the tree kind of helps illustrate how this code generation actually works. If I've got a program like this, I've got a program like this, a kind of simplified view of the parse tree would look something like this. I'm just going to call this an if statement that has an expression, a statement for its body, which contains two statements, a print statement and an assignment statement, and its else body just contains a single assignment. Well, maybe we call this a compound statement. Okay. Questions on this? This is a very this would be more like an abstract syntax tree, so I'm not writing out the whole parse tree. But any questions on that, this sort of simplified view of the expression tree or the parse tree? Okay, so this would be printing x. This would be assigning x to 1. This would be assigning x to 2. All right, and so recall that each of these nodes represents one of your parsing functions that will simultaneously parse, and then as a result will emit code corresponding to that. So for the if statement, all of this, well, this would actually be an expression. So recall that when trying to reason about how to parse and generate code for the if statement, you don't have to think about how expressions and statements and assignments are done, because that's all handled by nested calls to functions that will parse and handle code, generate code for those. So you only have to worry about the if statement. And the way the if statement works is you insert, if this parse tree is effectively the call graph of our parser, it inserts code just before we call the function that produces the body. We insert code after that body, and we insert code after the else body. So what code gets produced after we generate code for the expression, but before we generate code for the statement? What gets produced here? Any takers? So as a little cheat sheet, we can look at this. So in this LVMIR, so now you're all sort of reverse engineers here. Where is this code processed in that tree? Is it processed by the if statement? Is it processed by the expression? Is it processed by an assignment statement? what does this correspond to? Any takers? No? Yeah?
Before the estate.
Before, well, some of it is. Some of it is, yeah. So some of it's before the if statement. So I don't have the original, well, do I have the original program here? No, probably should have put the original program. Sorry about that. Well, you can see here that this comparison is definitely part of the if statement. So this here is the assignment statement. So this is saying get the value of x, load x, and then compare it to 10 to see if it's equal. So this is just saying x equals 10. So this part is the stuff before the if statement. When we start processing the if statement, that's here. This is the whole if statement. This is just dispatched to the expression, and then this is part of the if statement. Okay, anyway, so let me make this a little clearer here. So after we just dispatch the work of generating code for the expression, and then we have to emit a comparison, a branch, and a new label. So this label is for the if body. And this branch is either to if or to the exit node, or the exit label, or to the else body label. So this is going to be the if to either else or exit. So, okay. Make sense? Make sense? So you generate the expression, and then once you have the temporary variable for the expression, you can generate a comparison. And with that comparison, you can generate the branch, and then you generate the label for the body of the if statement. Questions on this? You guys are suspiciously silent. I don't know if that means you're getting it or totally not getting it. So ask questions, ask questions. Yeah. Well, you can bring notes. You can bring any notes you want. All right, so before, yeah.
How many pages of notes can you have?
I mean, I hate to kill lots of trees. I don't know, let's say 20 pages. How's that sound? Does that seem sufficient? Does that seem sufficient or no? All right, let's see. Yeah, somebody did that last semester, so I felt kind of bad doing that. Yeah, like 20 pages, I guess. How's that? Let's say 20 pages. So yeah, you can have all your references. You can have all your grammar and everything references. All right, so when we generate the expression, right, the if statement dispatches generating the expression. It tells you what temporary register that value is going to be stored in. So then the first part of the if statement just needs to generate the comparison, the branch, and the body for the if statement. Then once we dispatch the work of generating code for the body, then we need our branch and a new label, which is going to be the else or the exit, depending on whether you have an else or an if statement. And that's it. And then we just recursively call the statement parser and code generator. And finally, at the end, the if statement just needs to generate a branch and a label for the exit or end node. Questions on this so far? Questions on this? So when we go to generate code for this, as before, this is essentially a post-order traversal. Your recursive, anytime you do recursive functions, you're basically traversing a tree in some way, even though you're not explicitly having a tree in memory. All recursion is basically a tree of calls, and that's because of your call stack. So the first thing we do is we generate the code for the expression here, and that will look something like load x, and then do a comparison of, well, let's see, whatever syntax is, comparing x to 0. Questions on this so far? Question on this. So this is the expression. Oh, whoops, sorry. This is supposed to be part of the if statement. So this is the expression. We load x. Oh, wait. Sorry. So this is not compare. This is computing the result of this comparison. Sorry about that. That's your expression node. And now we are back inside of the if node. That's where we generate the comparison. So some temporary register, generate comparison. I think it was like, how do we do it? Not equal to 0. You're free to implement the logic however you wanted. I can't remember how I suggested doing it, but you can just compare the result. Check if it's not equal to 0. Is it not false? There. Law of the excluded middle. Is it true? And that's the comparison. Then generate the branch. The branch will be based on T3. It will branch to either the if body. So let's call this L1, or it will branch to, and just to save myself a little time, I'm going to leave out the labels. It will either branch to L1 or L2, and then we need the first label, L1. So in red is all the stuff that the if control structure is generating. So then once we've generated all this code here, what's the next thing that the if parser and code generator does? So we've called expression and we've emitted comparison branch and label. What's the next thing that happens? So we just recursively call the statement parser on the statement given the statement for the if body. So I won't write out all the code for this, but effectively, eventually, there's going to be a call to print integer, and there's going to be a call to store the assignment. That's what L1 is going to have. So once we've finished processing this whole tree, we're back inside of the if statement parser, and we process, or we start emitting code for the else body. So LLVM requires these blocks to end with a branch. So I'm branching to L3. So why is it L3 and not L2? Because we have an else. Yes, exactly. So we have an else. So if you have an if and then, you're only going to need two labels. If you have an if then else, you need 3 labels. And when you're writing project 3, you knew that because if you saw an else keyword, you knew that you needed to make a new label. Okay, so branch to L3. I'm going to move over here to the right. And here's our L2 label. Let me divide this a little bit. This continues. Yeah, that's ugly. All right, so there's our L. So we created our branch to L3, and we created our new label L2. So what's the next thing that the if statement does? Else body. So the else body is just recursively calling statement to do all the work for it. And when we do that, there's going to be some assignment, so there's going to be some kind of store instruction that gets emitted. And finally, the if statement will create a branch to the exit label and generate the exit label. And that's it. And so this is incomplete LLVM code. This won't compile, but you're guaranteed to have at least something after the if statement, even if it's a return, for instance. At least in the way we design simplicity. And if then you would have to ensure that that's the case. You'd have to automatically insert something like a return statement, even if the programmer didn't put it in. That's why I had told the graders to make the test cases so that the return was always at the end to make this simpler. Okay, questions on this? Questions on generating control flow statements? Yeah. The third statement? Here? In here? This is the comparison operation. So the way the statement is implemented in LVMIR is with a compare and branch. A branch takes some true or false value, effectively, and either branches to the first or to the second label. But this type is a one-bit integer, or true false. So in order to get a true false value, we need to do some kind of comparison. We need to do it. That's the whole point of the statement, is that we do a comparison, get the result of that, get the logical true false result of that, and then branch based on that result. Make sense? Yeah. In LOVM, yeah, you could do that. I think. The reason I suggested doing this is that it's just easier for compilation. Yeah, you could have done that. But this makes it easier to write the compiler because you can completely separate the if statement from expressions. You don't have to have yeah. I think that's because you don't have to assume that the expression turns out. Well, yeah. Anyway, either is fine. Depends on how you write your compiler. Other questions on this? Okay. Yeah.
So during the exam, you would want us to fill everything out properly, right?
Yeah. I mean, you can be a little hand wavy about the IR. You don't have to be precise about exactly what the LLVM will expect. Just get the main idea that you've got compare and branch, labels in the right place, branches in the right place, and you're good to go. Yeah.
So let's just print X.
Print integer 0. Where do you see that?
So in the comparison, if X equals 0, print 0.
If X is 0, I mean, that would be like an optimization. If your compiler can do that, then
Would that be wrong?
I guess it wouldn't be wrong. No, it wouldn't be wrong. Yeah, it wouldn't be wrong. Yeah.
How much are each of the sort responses worth?
Oh yeah, good question. I forgot to do that. Oh, I think everything's just 1 point each.
Oh, okay.
Does that seem okay?
All weighted the same?
Yeah, I think weighting the same because in the past I've weighted harder things more points, but that's actually intuitively that makes sense to me, but actually, yeah, that ends up making for bad grades. So yeah, I'll just weight them all equally. That just makes it really simple. So then you can kind of game the point schemes a little bit. All right, other questions? Other questions? All right, let's do stylus batteries. Okay. Fortunately, it's a quadruple A battery. That's convenient to find. All right, let's do types. So the next, one other thing that I'd like you to be able to do for the exam is be able to do the type checking algorithm. So let's, so be able to write write that expression tree and then annotate it with the types of each node. And so the kind of tricky thing to remember here is that the operands themselves, like every node on that expression tree has a type, including the operands. So for instance, if I've got a multiplication symbol, what is the type of that multiplication symbol? So, okay, even start simpler. If I have the ASCII symbol for the number 1, what is the type in simple C of that symbol? Huh? Somebody say 3? Is that what I heard? What's the type of the ASCII character 1 in simple C? It's int. Just int. It's int. It's not a trick question. It's int. So what about if I have the symbol x? What is the type of the symbol x in simple C? What's that? You check the symbol table. You check the symbol table. I mean, you could just sort of assume it's int because I've said everything is int. But in a real compiler, the symbol is defined. The symbol's type is defined by the programmer. You save that in a symbol table. When you encounter it in the program, you check the symbol table to see what it is. What if I have the symbol, asterisk, the multiplication symbol? What is the type of asterisk? You can call it out. All right. You can call it out. What is the type of asterisk? So that's an int. Look up in the symbol table. And what about the asterisk symbol? What is the type of the asterisk symbol? Close. So you can think of it as a function that takes two parameters, which are both int, and returns an int. So that's the way we can describe the type of this symbol. So even though the symbol is not, it's not a primitive type, it doesn't represent some range of values, it represents a function, something that takes some number of operands of whatever types they are. In this case, there are 2 integers, and returns another data type. So this is effectively the function data type. Okay, so knowing these 3 things, we can take any arbitrary expression tree from simple C, like say I've got x plus 1 times, y. X plus 1 times y. I'm going to be even more hand wavy about the expression tree for this. So this is what the expression tree, reduced to its core components would look like. There's, if you were to do the post-order traversal of this, x would be the left operand of the plus, the right operand would be the result of the multiplication. The multiplication would be the result of multiplying 1 and whatever the value of y is. So if we were to take this tree with its types, how does the type checking algorithm work? So we traverse the tree, how do we traverse the tree? What kind of traversal is it on the tree? Anybody remember the type checking algorithm? What's that? It's post order. It's all post order. Everything's post order. So yeah, so it's all post order. So in order to know the type of the top node, we have to know the type of its left node, the type of its right child. In order to know the type of the right child, we have to know the type of the left child and the right child. Perform the type checking on the parent, and then perform the type checking on the parent. Okay, so let's do this in post order again. So with compilers, it's all like post order tree traversal. It's like everything you do. So if you understand one post-order tree traversal, a lot of these algorithms are just different, variations of post-order tree traversals. All right, so the first node we look at is x. In order to know x, we look it up in the symbol table. So assuming that the symbol table, symbol C, they're all int. So we look up in the symbol table and we find that x has type int. And now we need to know the type of the right operand. Well, in order to know the type of this right operand, we need to know the type of 1, which is just by definition of simple C. If we have sequences of ASCII characters that are representing some sequence between 0 and 9, some digits. We call that int. We just define that to be an int. And for the right operand of multiplication, we look it up a symbol table and find that it's int. But how do we type check this node? How do we know whether this node is correctly typed? So we know it's, yeah. Right. So the multiplication has type pair of ints goes to int. So our type checking algorithm will just check, is the left operated int and the right operated int? If so, we know that the type of this node is an int. Questions on that? That's just the basic type checking algorithm. And similarly, the symbol plus has the same type signature. It takes 2 ints and returns an int. So in order to type check this, we look at its left child, which is an int. We look at its right child, which we've proven to be an int by applying the function type of multiplication to it. So we know that its resulting type is an int. And then we can conclude that the result of plus is also an int. Questions on this? Questions? Yeah.
So when we're doing the exam, is it going to be based off of the, is it going to be very generic on questions?
It's going to be like this, basically, like almost identical to this, where I say, here's an expression, do the type checking algorithm, and annotate each node of the tree with its type. Including the types of these symbols. You should know that these symbols have this function type. That's like, yeah.
How long do you think we'll take an exam?
I don't know. It's a good question. We'll find out. I don't know. I think it'll vary. I'll give you you'll have what did I say? 2 hours or
2 hours, yeah.
2 hours, I think. But I don't think it'll take that long. I think some people might be done in half hour. Some people might take full 2 hours. All right, let me do one more example of a tree and type checking a tree. So let's say we've got x plus y less than 0. Perfectly fine expression in simple C. Its parse tree will look something like this.
Could you change screen?
I can absolutely do that. Sorry about that. So we have a expression like this, which is perfectly valid in simple C. X, y, 0. So the top node is adding x, and whatever the result of y minus 0 is. This is something that is okay to do in C, but let's see what happens when we do this in simple C. So just like before, let's assume x and y have the same types. So x and y are both int. We know that 0 is int. But what is the type of this node? In order to know that, first we have to know the type of the symbol. So what is the type of the less than symbol in simple C? What's that? A Boolean? So it's almost. So just like, oh yeah, you can't see that. Just like the type of multiplication was not an int, whereas the type of 1 is an int. Type of multiplication is a function type. It's a type that takes some types and returns another type. So similarly, a less than symbol is not just a Boolean on its own. It's actually a function. But what is the type of that function? So it certainly returns a Boolean. But being a function type, what are the types of its parameters? So what parameters? What can its parameters be? In this case, so what are there other cases for less than sign where it's not an int? Okay, that's true. Yeah, that's a good point. So for simple C, I sort of let you just do ints That's an example, take programming languages. That's an example of like operator overloading, where the same symbol actually has multiple types. And then, depending on the design of the language, it's chosen automatically, or there's different symbols for it. But good point. Yeah, it could be, it could be overloaded to have multiple types. In simple C, it just takes 2 ints, returns a bool. And plus, as before, takes 2 ints and returns an int. So when we apply the type checking algorithm to this tree, what happens? We type check this node. We have to type check its left child, which is an int, and we type check its right child. We don't know its type yet, so we have to recursively apply the type checking algorithm. So we check the right child, which is an int, the right child, which is an int. And then what do we do to discover the type of this node? So not the symbol, but this node. So how do we know the type of this? What is the type of this node going to be? It's going to be an int, a bool, a float? A Boolean. Why? Why is it going to be Boolean? Because it takes 2 ints. Because this type of the symbol is it takes 2 ints, returns a Boolean. Int its left and right children are ints, so we can conclude that the type of this node is a bool. Okay, so continuing the type checking algorithm, what's the next thing we need to check? Now that we know the left and right child types for the plus operation, we find the type of the root node. Okay, so how do we type check this node? We look at its children, so its left child is an int, its right child is a bool. The type of plus is it takes 2 ints and returns an int. So what happens? We can't conclude that this is correctly typed. We get a type error in this case. Or in simple C, we get a type error. So it doesn't type check. We can't prove that this program is type safe, that it uses types properly. Yeah.
So if these questions were 1 point, is there partial credit on that 1 point?
Yeah, I guess so. It could be. Maybe. Do you feel you need partial credit?
You never know.
Okay. Yeah, I think for the open-ended, there'll be partial credit for the open-ended. Maybe like half point or a point. Okay, questions on that? So that's a type checking algorithm. It's effectively an automated proof. So if you ever sat in math class hating writing proofs, well, it turns out that you can write algorithms to do it for you to some degree. And so effectively, this is a proof because the leaves of the tree are our axioms. They're the things that are just like, oh, you just declare it to be true. X is always an int, 0 is always an int. And the inner nodes are the propositions. Like if I see 2 ints, therefore I can conclude. So this function type is equivalent to a proposition, like anything else in a proof. And if you can construct this tree, you can automatically prove that whatever it is you're trying to say is true. In this case, we're trying to say that the program is correctly typed, or we can find a type for the root node. So that's the proof that we're trying to do. But there are systems where you can actually write any proof you want that you can do in math. You can write it using a type system effectively. Okay, questions on this? Questions on type checking? So I'll just ask you to do exactly this. You just write an expression tree. Make sure you write out all the types, all the symbols. You don't have to write it like this. You can write it. If you're more comfortable with whatever grammar we used or whether it's the right recursive, left recursive, make sure it's operator precedence. But yeah. I don't. Oh, yeah. I think you're right. It does. Good point. Ooh, I wish you had told me that 10 minutes ago. I'll do a quick little hack here. Pretend you didn't see this. Okay. So I should go back and edit that, the magic of video. Yeah. Oh, wait. Wait. I'm sorry.
That would work, though.
No, this. Sorry. Oof. It's late in the semester. All right. Sorry, go ahead.
So when we're doing construction tests, are we assuming like the operator precedence that's been established?
Yeah. Assume it's simple C. Assume simple C. Yeah, assume simple C. So that was my mistake. Apologies for that. Yeah, can resolve it with a little hack. But yeah, I think, yeah. Other questions on this? Questions on type checking? Let's see. So symbol tables. Yeah, just be able to take a program and write what a symbol table would be. Should be, okay, who wants to see that? Who wants to see the symbol table structure? Okay, so let's look at that. So if we've got a program, if we've got a program like this, how do we construct a symbol table for this program? Let me, yeah. Sorry, so what's inside of the symbol table for a compiler, or at least for the simple C compiler? Everything.
Variable.
So what fields are in there? So the variable names are in there. What's that? Their type, their address. That's mostly what you need in a symbol table. Their scope. So that can be done inside the symbol table or sort of as a parent. Yeah.
Are we going to need form to give the address?
I'm sorry, say again?
Are we going to have to make up an address?
You can just make up an address. Yeah. You can just call it like that for X. All right. So if we're walking through this parse tree, we're parsing this function, this simple C program. When we encounter a declaration, what happens to the symbol table? What does the declaration do to modify the symbol table? Yeah, we add it to the symbol table. So whatever the symbol name is, that becomes the same. Whatever the type is, that goes in our type field. And when we're generating code, we have to allocate an address for it. LLVM makes that super simple. We just generate code for a load and make up a new temporary register. So similarly, when we get to the second declaration, we also add that to the symbol table. And so when we see X, how does that modify the symbol table? When we see this X plus 1. It doesn't modify the symbol table. Actually, it's not complete. It doesn't do anything. What about print X? How does that modify the symbol table? Doesn't modify it. Get into the program. That's a symbol table for this code snippet. Pretty straightforward, right? Yeah.
So we're not writing any code for this.
No, I'll just ask you, it'll be separate. It'll be like, here's a program, write code for it. Here's a program, write a symbol table for it. Here's a program, do the type checking. It'll be all like sort of separate questions on the same snippet of code, really. Oh, yeah. So we'll also ask you about some of the program analysis and optimizations. I won't make you write the algorithm or sort of execute the algorithm, but you should be aware of like live variables, dead code, available expressions, and common subexpression elimination. All right, so who remembers the relationship between whatever right here, between live variable analysis and dead code elimination? Does anyone remember like these two things, relationship between them, which is which, what are they? So live variable analysis. What is live variable analysis? Yeah. It's backwards, but it is information about what's next in the program. So all the live variable analysis is just saying for each point in the program, that was weird. So at each point in the program, so let's write a little program here, or actually, let me get the slides for this.
Is the recording still good?
What's that?
Is the recording still good?
Oh, good question. Yeah, and I have a backup of the audio. So, oh no, this was optimization. So this was, so I'm only going to ask you about live variables and dead code elimination. So where was this? There's dead code. It's available expressions, liveness analysis. So remember, liveness analysis was just at each point in the program, what variables could still be used at the end of the program. So if you've got a return statement, if it says like return B, then that's going to be live at the end of the function or whatever snippet of code it is. And as you move backwards through these statements, you just keep updating the list of variables that can be live. So in this case, A became live and D ceased to be live as we moved backwards. So when we moved from this point in the program to this point in the program, D was removed and A was added. So why? Why is D removed? Anybody? Yeah. Because D is about to be assigned. So if D is going to be overwritten, then any point before it, whatever value D was assigned to, doesn't matter. It's never going to be used. Why was A added? Because it was used. Yeah, because it was used at this point. So even though after this point, A is not live because it's not being used anywhere, because it's being used here, it must be live before that point. It's all just like definitions and uses. It's just sort of tracking the definitions of uses of variables to see like, is that assignment being overwritten or not? Is that variable that you assigned actually being used or not? So that's the live analysis. So the live analysis is the program analysis that underlies optimizations. So to do optimizations, you first need to do some program analysis. Remember, it had to be sound analysis to make sure you know about every possible the liveness for every possible run of the program, for every possible input of the program. And once we have this information, once we have done this liveness analysis, once we know at every point which variables are live or not, then we can apply our optimization. So the dead code elimination was like the optimization that you could do with this live variable analysis. So dead code elimination could just remove any assignments to variables that were never going to be used at that point. So because D is reassigned here, actually it's used here as well. So let's see what gets removed. So because F is never used after it's assigned, we can remove it. D, isn't D? Oh yeah, D is part of the return values. And so because C is never used at this point, C is never used after this point, it can also be removed. Questions on this? I know I went through that, reviewed that really fast, but yeah.
And so we'll be given the starting statement for the live variables, like which ones we assume are live.
Right. You can, yeah. It'll be the return statement. Whatever's being returned, that's what's going to be live. Yeah. It's going to be a simple C program. With branching. So the branching stuff was in the global optimization slides. So this slide. So basically when you've got two successor nodes, what does it mean for the predecessor? Well, you just take the union. So if only B, C, and D are live along this path, and A, B, C, and D are live along this path, you union the set of live variables. So even though at runtime this path may never actually be taken at runtime, we don't really know that yet at this control flow graph level. We just assume that both paths can be taken. That's the soundness. That gives us soundness. Yeah.
So we leave assignments to variables that aren't live and to
Yeah, that's the dead code elimination. Yeah, that's what it's used for. So a couple other questions. If we want to prove a program does what it says it does for every possible input, can we just run the program for every possible input in general? Why can't we do that?
You can do the not of it, right?
You can do the not of it.
Or no, wrong thing.
What's that? You might have infinite inputs, and the program may never halt. The program may never run forever. And stack smashing. How does the stack smashing attack work? How did we take control of the target computer? Yeah, we overwrote the return address. Which register was that stored in? That's the instruction pointer or the program counter. So the return address goes to the instruction pointer and the program counter. Let's see, sound analyses. So if my analysis is sound, can I have false negatives or false positives? Neither or both? Everybody remember this?
You can have one or the other. I can't remember which one.
So you will get false positives if your bug finder is written that way, but not false negatives. If you have a complete analysis that's not sound, the reverse. You can have false negatives, but not false positives. So, review that lecture to see the kind of reasoning behind that. Do you remember the 3 AUs, the 3 golden things? Authentication, authorization, audit. What about the CIA triad? What are those 3? You should all know it. Integrity, availability. Okay, good. Okay, I think that's everything you need. So you can review these 2 lectures. Go over, of course, those lectures. You can look at this sort of loose practice exam here to see exactly the content that's going to be on the exam. All right. See you in 2 days.
At the same time as class?
Yeah, it is. And here.